So now let's look at a couple of examples for sites. The most important one at the beginning is the one that shows that sheaves on a site are actually just a generalization of sheaves on a topological space. So I had better make the open subsets of a topological space X into a site. So let X be a topological space. Define the category X as follows. The objects are the open subsets of X, so the topology of X, and for U and V in X open, let the morphisms in X between U and V equal the inclusion U into V if U is a subset of V, and so the set containing the inclusion if U is a subset of V and just nothing otherwise. And define a collection from Ui to U, I and I, to be an open cover or cover if all of the Fi are morphisms in X Ui to U, meaning that they are inclusions of subsets, and if the union of all of the images in U are actually equal to U. So just the usual notion of a cover. Then, well, I guess I already illustrated that it satisfies the composition and the weak pullback property. So this notion of a cover indeed defines a coverage. Defines a coverage of X. Thus, X is a site called the small Zariski site. Of X. Now for the example that is most important for our treatment of vector bundles, the category man of manifolds. So define man by, well, the objects of man are manifolds, smooth manifolds to be precise. And morphism between two manifolds X and Y are smooth maps. And now we are trying to make this into a site, so we have to describe what a cover is. And now we're going to do something slightly different. Well, one way is we could just do the same thing as we did for the Zariski site. A cover is just a cover in the usual topological sense, but for manifolds it's actually a bit wiser to use a slightly different notion, or to be a bit more restrictive about what we call a cover. So a family Fi Ui to U I and I is called a differentially good cover if firstly the Fi are inclusions of subsets, then the Ui and U are open subsets, or let's say a cover in the usual topological sense. and if all of the UI are diffeomorphic to open balls in Rn. And most importantly, not only are all of the UI diffeomorphic to open balls in Rn, all finite intersections of UIs are either empty or diffeomorphic to open balls. Now the question is, does this form a coverage? Firstly, does every manifold have such a differentially good cover? The answer is yes, but that's not straightforward. But essentially it boils down to we can cover every manifold by charts, so by open subsets of Rn. So ultimately our question reduces to, does any open subset of Rn have a differentially good cover? And you can show that that is indeed the case. So every object has a cover. Check. Second thing is, do they compose well? And, well, yeah, we're just dealing with inclusions, so there's nothing really to check. And thirdly, this partial pullback property, why is that satisfied? Well, if you pull back a differentially good open cover, you just get an open cover, and then you can refine that to a differentially good open cover. So partial pullbacks. Yes. So, conclusion, category man of smooth manifolds equipped with differentially good open covers is also a site. Namely, the site that we are going to talk about when we are talking about vector bundles. And lastly, one example that very often pops up just because we need sites to talk about stacks, and stacks are usually used in algebraic geometry, so that better also be a site of schemes. And one site especially that is very interesting usually is the fppf site of schemes. So first we define the category SCH of schemes by, the objects are schemes, and the morphisms between two schemes X and Y are, morphisms of schemes. And we now define the fppf site by saying that family fi from ui to u indexed by I is called a cover if firstly, the usual condition of the images indeed covering u. Secondly, the fi are flat morphisms of schemes. And thirdly, that the fi are locally finitely presented. This defines a site called the fppf site. The site fppf, where fppf stands for fidèlement plat de présentation finie. So faithfully flat and of finite presentation. Faithfully flat means that the fi are flat and that they are surjective, or at least collectively surjective. and présentation finie, finitely presented, corresponds to that thing there. And this site is interesting because you can define the stack of quasi-coherent modules on that site, and it also turns out to be a stack that is sort of the algebraic geometry equivalent of the stack of vector bundles that we are trying to reach.